Good day, students. Welcome to mathgoodserve.com. In this clip, we are going to be going over problem number 9 of our Unit 4 test on the application of derivatives. In this clip, we're going to be focusing on concavity. All right, so for question 9, we are to find where the function is concave up and concave down. For the function f of x equals x divided by 1 plus x squared. All right, so before we go ahead and solve the problem, let's refresh our memory on how to determine the concavity of a function. Okay, so if f double prime, the second derivative is less than 0, um, the function is going to be concave up. Okay, so if f double prime is less than 0 or negative, then the function is concave down. Concave down. Okay, and then if the second derivative is greater than 0, then the function is going to be concave up. All right, so don't forget negative means downward facing concavity for the second derivative, okay? And if the second derivative is positive, that means upward facing concavity. All right, with that in mind, let's go ahead and solve the problem. So what are we looking for first? We need to find the second derivative, set up intervals where it's equal to 0 or where it's undefined, and look for what happens between those boundary points. Okay, is it positive, negative? That tells us the concavity. Now, the function f of x is x divided by 1 plus x quantity squared. Now this is a quotient of two functions, so we are going to be using the quotient rule here. All right, so the quotient rule is, to remind ourselves, u over v prime is equal to v u prime minus u v prime, okay, divided by v squared. So in this problem, x is u, and the denominator 1, the quantity 1 plus x squared is v. All right, so f prime, the first derivative, is going to be v, which is 1 plus x quantity squared times the derivative of x minus u, which is x times the quantity 1 plus x squared prime. All right, and then that's uv prime, and then we divide that by v squared. So we'll have 1 plus x quantity squared. All right, let's go ahead and differentiate. We have f prime of x equals 1 plus x quantity squared. Now, x prime is just 1. And then we can times 1 minus x. Now, when we are differentiating 1 plus x quantity squared, we're going to be using the chain rule. The outer function here is x squared. Its derivative is 2x. And the inner function is 1 plus x, and its derivative is just 1. So we're going to evaluate the derivative of the outer function at the inner function. So we're going to take this and plug it in there, and then multiply it by the derivative of the inner function. Okay, so applying the chain rule here, we're going to have times 2 times 1 plus x to the first power. That is the derivative of the outer function, x squared, evaluated at the inner function, 1 plus x, times the derivative of the inner function, which is just 1. Okay? Right, and then we're going to divide this by the square of the denominator using the power over power property. We're going to have 1 plus x quantity raised to the 4th power. Okay? You just multiply the exponents whenever you raise a power to a power. All right, let's simplify it a little bit more. So we're going to have a 1 plus x squared is simply 1 plus 2x plus 1 minus, we'll distribute 2x to this quantity here, and we'll have negative 2x minus 2x squared. Okay, let's see, make a real quick correction here. This is plus x squared. All right, so we have the numerator expanded out completely. Let's see if we can combine like terms. So in the numerator, the 2x's, 2x and negative 2x add up to 0. So now we are going to have, let's see, f prime of x f prime of x is equal to 1. X squared minus 2x squared is negative x, negative x squared. And we have that divided by 1 plus x to the fourth, quantity 1 plus x to the fourth. Since this is a difference of squares here, we can factor it, right? We can factor it into 1 minus x times 1 plus x. And we'll divide that by 1 plus x to the fourth. So you can see that we can make a reduction here. We can reduce this. We can cancel out one of the x, 1 plus x, one of the 1 plus x in this 1 plus x to the fourth with a 1 plus x to the first power in the numerator, okay? So this, you just subtract the exponents. This gets reduced by 1 to 3. Okay, so we have f prime of x equals 1 minus x over 1 plus x to the third. Okay, now what are we going to do next? Well, let's go back to the beginning. Remember we said to find the concavity, we need to look at the sign of the second derivative. Okay, what do we have? We have the first derivative. So we're going to do what? We're going to differentiate again. All right. Now, we're going to use the quotient rule again. This is u, the numerator, and the denominator is v. We remember what the quotient rule is. U over v prime is equal to vu prime minus, so vu prime minus uv prime divided by v squared. All right, so let's go ahead and apply that here. So the second derivative, f double prime of x is equal to v, which is 1 plus x to the third, times u prime, 1 minus x prime, minus u, which is quantity 1 minus x, times v prime, which is 1 plus x, quantity raised to the third, prime, divided by the denominator square, v square. Okay, so that is going to be 1 plus x raised to the third, square the entire quantity. Okay, all right, so that's how we'll find the second derivative. So let's go ahead and differentiate and then simplify. F double prime of x is equal to 1 plus x to the third. Now the derivative of this is just negative 1 minus 1 minus x. We're going to apply the chain rule here again. Differentiate the outer function, which is x to the third. It's going to be 3x squared. So we have 3 times, instead of x, we plug in the inner function, which is 1 plus x. So this is 3x squared evaluated at the inner function, which is 1 plus x, x squared. 1 plus x. All right, so we have that. And then we multiply it, of course, by the derivative of the inner function, which is just derivative of 1 plus x is 1. All right, so we have that divided by the denominator square. So denominator square, we have 1 plus x quantity raised to the third power. Actually, let's just simplify that. We just multiply the powers. So 3 times 2 is 6. Okay, now we're done differentiating. Let's go ahead and simplify. Now, if you notice, I have a 1 plus x to the third here and a 1 plus x squared. So I can factor out the GCF, which is 1 plus x to the second power. The smaller of the two factors with identical bases, okay? So we have 1 plus x to the second power, and then we're left with, let's not forget this minus negative 1 plus x, and then minus 3 times 1 minus x, okay? And then we'll divide by 1 plus x to the 6th. All right, now you notice that these can be reduced, right? You just simply subtract the exponents using the quotient property of exponents. And then over here, we can just distribute and then simplify, okay? So let's go ahead and reduce this. 1 plus x squared goes here once, and this one just reduces by 2. You subtract 2 from the power here, which is 4. And then we can distribute this negative 1 and then the negative 3 also. So we're going to have negative 1 minus x minus 3 minus 3x. Okay, this becomes plus 3x. All right, and then that divided by 1 plus x to the 4th. All right, almost there. We just combine like terms on the top, and that will give us the second derivative. All right, so second derivative of x is given by, let's see what we have here, 2x minus x plus 3x is 2x minus 4 divided by 1 plus x to the 4th. All right, so now what we're going to do, we're going to look for where the second derivative is 0 or does not exist, and then we're going to use that to set up our boundary points, okay, our boundary values. So we're going to look for where f double prime of x is equal to 0 or where f double prime of x does not exist, because this are possible boundary or values where the sign could change, okay? All right, so where is it the second derivative equal to 0? You set the entire expression, second derivative, set it equal to 0, and you solve, all right? So to solve this, you cross multiply. You have 2x minus 4 equals 0. When you solve for x, you end up with x equals 4 over 2, 2. When is it undefined or non-existent? You set the denominator to 0. All right. Raise both sides to the 4th root. So the 4th root of both sides. And then we're going to have 1 plus x equals 0. And x equals negative 1. All right. Okay, so what are we going to do now? We're going to draw a number line and use the sign of f double prime to determine the behavior of f. Okay, so we have negative 1 and 2 boundary points, and then we have 3 intervals: interval 1, interval 2, interval 3. Now we want to look for the sign of f double prime on these 3 intervals, and that will tell us the behavior of f on those intervals. All right, so let's go ahead and partition the intervals so we can clearly see what's going on. So this is the first boundary point where there might be a sign change, it's not guaranteed, and this is another boundary point. If there is a sign change, this is just by the way, and the point is, and the function is differentiable at that point, the second derivative is defined, then you have a point of inflection there, okay? All right, so let's go ahead and see what happens. Um, for the first interval, we can pick a value, x equals -1. In the second interval, we can use 0. Third interval, we can use, how about we just use 3? All right. Okay, so let's see what the sign of f double prime is. So for interval 1, we are testing x equals -1. The second derivative, f double prime, is 2x minus 4 over 1 plus x to the fourth. All I care about is the sign. Okay, so I know that if I raise any quantity to an even, power is going to be positive. So I don't even need to bother about the denominator because I know that the denominator will always be positive regardless of what I choose. Okay, so in the first interval, what are we going to have? We're gonna focus our attention on the numerator. If I plug in -1 in the numerator, so I'm going to have 2 times -1 minus 4 over the denominator, which is already positive. So what is this going to be? It's going to be a negative over a positive, which is negative. All right, so it's going to be a negative sign, which is all I care about, so it's negative on this interval. All right, interval 2, x equals 0. We're going to have 2 times 0 minus 4 over a positive number. All right, that's going to give us a negative result divided by positive, which is negative again. So we have a negative sign on interval 2. And then lastly, we have at 3, x equals 3. We're going to have 2 times 3 minus 4 over a positive number, which yields 2 times 3 is 6, so it's bigger than this, so it's going to be positive. Divided by positive is positive. So we have a positive second derivative sign on interval number 3. Okay, let me line my signs up properly. It's all over the place. So we have sign of the f double prime is negative, negative, positive. So what does that tell us about the behavior of f? Remember the rule, if f double prime is negative, f is going to be what? Concave down, right? And if f double prime is positive, f is concave up. We talked about this earlier. So it's concave down, concave down, concave up. All right. So let's go ahead and write down our answers. So f is concave up on the interval 2 to infinity, and f is concave down on the interval -infinity all the way to -1, union -1 all the way to 2. Okay, so there goes the concavity of our function on the real number line. Thanks so much for taking the time to watch this presentation. We really appreciate it. Feel free to subscribe to our channel for updates to other cool tutorials such as this. And do give us a thumbs up if you appreciate this presentation. We appreciate it. More clips can be found on mathgotserved.com. Thanks again for watching and have a wonderful day.